Assalamu alaikum, and the second part of lecture number 8, and this part is about the flow of electromagnetic power. The electromagnetic waves carries with them electromagnetic power, which transport or transfer energy from one point to another, and this is how we transfer information or power or like signals. And we need to know like the relation between the waves and its power. Okay, we are starting by, as usual, by Maxwell's equation. So we have here Faraday's law and Ampere's law. Here we look for the cross product of the two fields and to its gradient. So the relationship here, the divergence of E cross H equal, similar to like the distribution of differential operator on two functions, equal the first function, curl of the first function, dot product with H, minus the curl of the second function, cross dot product with E. So this is like a new vector algebra relation. So here you can notice that like this blue term is from Faraday's law, the red term is from Ampere's law. Just substituting, we'll have the divergence of E cross H equal H dot time derivative of B minus E time derivative of D minus E dot J. Also, you should notice that H and B are related, B equal mu H, E and D are related, D equal epsilon E, J and E are related, J equal sigma E. So if we substituted those like relation between B and H, D and E, J and E, we'll have this expression. We can just do this, you do the math, we can put the H inside and have half, because now we are making a derivative for H square, and this can be done because of the time harmonic functionality of the signal, because we are assuming the signal depends on time with e to the j omega t. So you can just review the math for this part, same for this part, and for this part this is like straightforward. We have like sigma, which is a constant, and we have E dot E equal E squared. So now we can rewrite this equation in this format and then like have this expression here. Now we can apply the divergence theorem to the two sides. So the divergence theorem, if we integrate like two sides, both of them to the volume, if we choose any volume that is enclosed by any closed surface, and we integrate both sides with respect to V, the right hand side will look like this. The left hand side, we can apply divergence theorem to it, and it will have this expression. Now looking into those terms, this term, as we studied before, is the total magnetic energy. Here, like because we are integrating with respect to volume, this is the total magnetic field inside the selected volume. Total magnetic energy stored in this volume. This term here, as we also studied before, is the total electric energy stored in the same volume. So those two terms integrated over volume is the total electric and magnetic energy stored in the volume. The time derivative means the rate of change with the negative sign. It will be the rate of decrease. So this is the rate of decrease of stored magnetic and electric energy in that volume. The second term here, we also studied this before in 303. This is power loss because of the conductivity or because of the free charge. So because of the conductivity of the material, we have some ohmic losses as heat into this volume. So here, this term is the total decrease of the stored energy, and this is the power dissipated in this volume. So having said that, the equation will look like this. The right hand side rate represents the rate of decrease of energy stored in the volume minus heat dissipation. So the left hand side should be something. The difference, the total decrease, goes in two things. Number one, power dissipation. Number two is the left hand side. So what is the left hand side? Now we can recall the conservation of energy. From the conservation of energy, the power inside the volume must be balanced. The amount of power decreasing in this volume must go out. There is no other way. So the decrease in energy stored in the volume, part of it goes like to heat dissipation, and part of it, if this is like the difference is not zero, so the remaining must go out of this volume. So the remaining part is the outflux or outflow of power from this volume, and this vector on the left hand side is called Poynting vector, which is E cross H. Its unit is watt per meter square. So it's the power density, the outflow of power density from surface S. So the Poynting theorem is stating that P dot ds, Poynting vector dot ds, here we just like have the negative sign. It can be in this side or on that side. So it's equal the rate of increase here, because it's a positive rate of increase of stored energy, electric and magnetic, within this volume, plus the power dissipated inside this volume. So this is the Poynting vector, and we got this from the physical meaning of this term and this term, plus the conservation of energy. Okay, so we have like two different forms to express E and H. We said like the phasor format, which is like this one, and we know that the time dependence is implicit, and the other format is the instantaneous format, or like the real part. So far in our course, except for one case when we talked about like complex intrinsic impedance, like we can use any of them interchangeably, and now we need to be careful when to use like this instead of each other, and where we need to use like a specific form of them. So if the operations that we have on the field is linear operation, so we add two fields, we like subtract two fields, we multiply by a constant, we divide by a constant, which is like a real constant, then we can use this one or that one like similarly. Okay, so here if we are multiplying or dividing by real constant, then we can use either form. But if we have any nonlinearity in the operation, like dividing by a complex or like multiplying two vectors, then we must use this format, so the instantaneous format. So here, like we have the Poynting vector equal E cross H. So Poynting vector is the real part of E cross product with the real part of H. This doesn't equal the real part of the cross product. They are not equal, and you can just verify that. So we can do the first part, the cross product of real part and real part, it will give us an expression. If we do the multiplication and add like the time harmonic implicit term to them and take the real quantity, it will be different. So this expression is not the correct one. The correct expression is the real part of E cross product the real part of H. So let us have this example, like quick example, like we want to find the Poynting vector at the surface of a long conductor circular wire, conductivity sigma, radius V, and it carries direct current I. So direct current, steady state current. So we can find J, which equal the current density I divided by the cross section. We know that E equal J over sigma. So we have the expression for E, and E in this case along the direction of the current. We assume this wire is like on the Z axis. H generated at the surface, we can also like from Ampere's law, equal A phi current divided by the circumference of this wire. The Poynting vector would be AZ cross A phi, which is in the direction of minus AR, so it is going in the conductor, and we have this expression. So to calculate the power per length, we will integrate over a cylinder of length L. So the current is going in the AR direction, so just from the side, dot product with the top or the bottom equal 0 because it's AR, dot AZ will equal 0. So just on the surface of the wire, we'll get the expression, and we'll have, just like do with the math, you will find that equal to I square R. So the Poynting theorem is here like verified the Ohm's law, that we show that the power going in the cylinder equal the amount of heat dissipated inside the conductor. So this is just like a simple and quick application of the Poynting theorem on this case of steady state current. So the Poynting vector is not just like for electromagnetic waves, it can also be like applied on steady state cases like the ones that we have in this example. So we have like the expression for Poynting vector, we call it like instantaneous. Instantaneous means that we see the power expression as a function of time. And you can see, of course, it is like very fast. And in practice, we don't really need to like follow this very fast variation of the power flow. We are more interested in the average power flow. And when I say average here, I'm saying average over time, because now it's like a fast sinusoidal, it's twice as the wave. So each wave is omega t, this one is 2 omega t. So the average here, we are averaging over a period of 1 period, 1 over f. So it's a time average over 1 period. And if you go for the expression, you will find that it is, and this is one of the times we can use this one is the RMS of this signal. So that's why also like another reason why people might use RMS, root mean square power of the signal, because it is related to the average power transfer by the wave. So another example about Poynting vector and electromagnetic waves. So for the following electric field, it's an electric field in the theta direction, and you can see it is propagating along the R direction. So this is called spherical wave. This wave is generated from a source at the origin and propagating in free space. So it's a wave. This is like spherical wave or expression of the wave in spherical coordinates. It is in the R direction from the origin. We want to find the expression for the magnetic field. We need to find the expression for the instantaneous Poynting vector. We need the average total power radiated by this source. So this is a source at the origin. This is the electric field radiated from this source, and we need to find those three requirements. As usual, I would recommend that and advise you try to solve this problem yourself, then continue the video. So please pause the video now and try to solve it yourself. Hopefully enough of you get back from the pause, and now let us watch the solution together. We know that from the relation of E, direction of propagation, and H, that H equal AR cross the direction of E, because this is TEM wave or plane uniform wave, and here the plane is a sphere, so that's why it's called spherical wave as well. So this equal 1 over eta naught, because it is saying here it is at the origin in free space, so that we know all the constitutive parameters are of free space. So this is real. So the expression for H is in the A phi direction, and we can just get it right away from that of the electric field. So eta naught for electric field is 120 pi. So we just divide by this. We'll find that we have 2. So you can just simply go over the math and we'll find this correctly. Okay, so the Poynting vector, the instantaneous expression, is the real part of E cross product with the real part of H. And we can just do the math. You will find it does have this expression. It's sine square omega t minus beta r. So the instantaneous Poynting vector, we can just expand sine square into 1 minus cosine. You can just also do the math for this. And we can now calculate the average Poynting vector, averaging over time, and we get this expression here. This is the second expression or third expression. Yeah, second expression. The third one is the total average power that is transferred from this source. This source is at the origin and it is transmitting power in all directions. So to calculate the total power radiated, we integrate over any closed surface. And the easiest, because of this expression, is over a sphere. So we choose any sphere of large radius r, and you integrate the average, because we need the average power radiated. We calculate the average power, which is a function of r dot ds. We have the expression for the average Poynting vector, and we integrate with respect to ds, which is of a surface. It's r squared sine theta d theta d phi. We do the math. It's straightforward, and we get the expression for that, which is the total average power radiated by this source. So at the end of this lecture, we have homework 5. It's due in 2 weeks, because next week we'll have a quiz. So I give you some more time to solve this homework. and I recommend that you review the learning objective and make sure that you learned all the points in this slide from this lecture. Thanks everybody.